Next of the quantities we're going to look at is the ohm. The ohm is a measure of resistance to flow. It's actually named after a German scientist. His name was George S. Ohm. He studied electricity back in the 1800s. And in terms of our water analogy, if you've ever taken a hose and squeezed it down, you're reducing the amount of flow, right? So that reduces the amount of flow that goes through because you're increasing the resistance. Materials that are insulative have a high resistance. Materials that are conductive have a low resistance. All materials, though, have some level of resistance. Last of the quantities we're going to look at are watts. Watts are essentially a measure of power, right? So they're going to be the amount of essentially energy that gets used up to do an electrical function of some type. They're named after the English scientist James Watt. He did a number of things, including developing the steam engine. And in terms of power, we're always going to be having a quantity representing essentially the rate at which something's done and the effort required to do it. So for example, in our water analogy, the rate is gallons per minute. That's the flow rate. And the effort would be the pressure, or PSI. Combine those two things together, that tells you how much power is required. And actually, you can measure, even in water systems, you can measure power in terms of watts. In terms of electrical systems, however, we use amps. Again, remember, amps is the amount of coulombs that pass by in a given second. Volts, of course, is going to be the resistance across it. So when we take our flow and we take our effort, when we combine those two together, they're going to give us watts. So 1 amp times 1 volt equals 1 watt. Now this is actually showing a resistor here. You probably noticed, but if not, when a resistor prevents electrical flow, the energy has to go somewhere, and generally it goes into the form of heat. This is showing a resistor heating up, and the heat coming off this resistor. The amount of wattage, or the amount of power used up to push current across this path, is going to have to be dissipated in some way, and that would be a measure of how much heat was generated. Now, if we take a look at it, keep in mind we have both US units, or what's referred to as imperial units, and SI, or metric units. For example, in our US units, we use horsepower. That's equally equal to about 750 watts, or 746 watts to be exact. Horsepowers are 550 foot-pounds per second, right? Because keep in mind, power involves a force times a distance divided by time. We could flip this around, that 1 watt is equal to 0.0134 horsepower. 1 watt is also equal to 3.412 BTUs per hour. BTUs are British thermal units. Right, and we can continue with these joules and watt second, etc. Now, one of the nice things about this is, if you take a look, when we have watts seconds, it's 1 to 1, right? Unfortunately, in the US unit, none of them really work out that nicely. We have numbers like 746, 550, etc. But in a lot of the metric units, it's 1 to 1. Now, I wouldn't waste your time memorizing this. This table is in your book. Also, probably most of your calculators have these types of unit conversions involved. But you do want to have a good sense of the difference between, say, for example, a horsepower and a watt. So when you do a calculation, you don't get these two confused. Suddenly, 1 horsepower equaling a very small number of watts, or vice versa. The most important law that governs the way electricity works is known as Ohm's law. And essentially, it relates voltage, current, and resistance. And what Ohm's law says is the voltage, or potential, is going to be equal to the current flow, where the amperage times the resistance. So E is equal to I times R. You'll also see voltage written with a V, that V is equal to I times R, but it means the same thing. Now, this works very nicely in a DC circuit because we're moving in one direction. And in DC circuit, we can say that 1 volt will push 1 ampere across or through 1 ohm. right? And essentially, we can then show that in terms of our flow, our current flow, it's going to be inversely proportional to resistance. The higher resistance, less current, et cetera, et cetera. And this formula can be manipulated in a few different ways. Right. Commonly, we use this voltage chart, right, that says the E is going to be equal to I times R, right? And we can use this in a few different ways. So, for example, if we have voltage, right, if you cover the portion of the chart, voltage is going to be equal to I times R. On the other hand, if you had current, you can cover the current, right? In this case here, the I is our measure of current. That's going to be equal to E divided by R, again, E or V, voltage divided by resistance. And if you want to solve for resistance, you could take your voltage using the symbol E divided by your current flow, or I, so E divided. So this chart is a quick way of combining Ohm's law and getting the various forms used to solve for that. A similar chart's available for power, right? Power, as I said, involves voltage times current is equal to power, but keep in mind we have all these other forms. So for example, if we had current and resistance, we could say that power is equal to current squared times R, right? Because keep in mind IR is equal to E. Or if you had voltage and resistance, you could have voltage squared divided by R is going to give us power. Similarly, if we want to solve for current, it could be power divided by R, the square root of that, I should say, or power divided by voltage, or in this case here, current divided by resistance. Many, many different forms, right? I don't suggest you memorize these, but you should definitely know that power is equal to voltage times current. And of course, the relationships that make up Ohm's law that brings all of these other ones together. So know that relationship and know how to manipulate it. So one of the things that's important to understand when we're dealing with electricity is metric prefixes. The fact is in metrics or in SI units, instead of showing multiples of something, we use a prefix to show. So for example, if you wanted to say it was 10 meters, you could say it was a decameter. If you wanted to say it was 1,000 meters, you could say it was a kilometer, a kilometer, right? And in fact, there is a metric prefix for every power of 10. We don't actually use all of these in engineering, however. We always just use factors of 10 to the 3 or 1,000. So take a look at here. If we have 1,000, it's kilo. If we have 1,000 times 1,000 or a million, it's mega. 1,000, 1,000, 1,000, or 10 to the 9th, it's giga. Tera is 10 to the 12th. Milli, 10 to the minus 3. Micro, 10 to the minus 6. Nano, 10 to the minus 9. Pico, 10 to the minus 12. So spend some time getting familiar with these. You will notice that they have a pretty standard symbology, where the ones bigger than the base unit use capital letters, ones smaller than the base unit use lowercase letters. Unfortunately, kilo snuck in here. And as a little guess, if anyone wants to email me why kilo is not capital K, potentially give you extra credit, so send it my way. But kilo is the only one that really jumps out at there. Micro, squeezing in a Greek letter is also a little bit problematic, but micro had always been defined as this mu here. So pretty standard symbols, though. Spend some time learning these. Another important aspect of studying electrical machinery and electricity in general is understanding the SI system. This is in part due to the fact that electricity is a relatively new phenomena using electricity, and as a result, we don't have two systems for studying it. Pretty much it's governed by the SI system, and the SI symbols and SI quantities are used in both the US and around the world. So if we take a look, here's a list of the various SI properties or quantities. Hopefully you're familiar with things like meter, kilograms, seconds. We definitely need to understand what amps are, right? That's electrical current. Uses the symbol A. Rest of these, not so much, but null, candle, radian, etc. All things that probably come up at some point in your engineering studies. Continue on. Hertz will come up. Frequency, that's the amount of things that happen within a given second. Also should be familiar with Newton, Pascal's, joules. These are all different types of force, pressure, energy. Again, getting back to electricity, we have watts. Watts are used in all different types of power, not just electricity, but we definitely use it in electrical calculations. They use the symbol W, it's equal to a joule per second. We also have coulombs, capital C, that's an amp times a second. We have volts, which is again a measure of electrical potential. We use V for those. Again, that's watts divided by amps. That's just Ohm's law. Capacitance will come up when we talk about capacitors. Electrical resistance, right, is ohms, measured in ohms. We use a Greek letter omega here. That again is volts divided by amperage. That's another version of Ohm's law. We'll also get into conductance, magnetic flux, etc., inductance as we go through the semester. But for now, definitely no ohms, definitely no coulombs, definitely no volts, definitely no amps. So to summarize, a coulomb is a measure of charge. It's equal to a little over 6 times 10 to the 8th electrons. Amps is the rate at which that charge passes by, so it's a measure of electrical current. It's equal to a coulomb per second. In terms of that, we use the letter I for this. It's referred to as the intensity of the current flow. So if you're confused a little bit why we use I and A, think of I for intensity. It's a measure of amperage in our Ohm's law calculation. For voltage, that's going to be our potential difference, right? So it's referred to as electromotive force, or if you want to think of it from the water perspective, electric pressure. It's generally going to be represented by a V. Oftentimes in Ohm's law representations, it uses an E. Again, both think of E for electromotive force, V for voltage. Ohms, there's that Greek omega. It measures the resistance, so how hard it is to push through current through a material. Watts are capital W, and of course the amount of power, right? So in this case, it would be amps multiplied by watts, or I'm sorry, amps multiplied by volts. So current times potential. And we'll see it uses the symbol, as I said, W oftentimes, but most often you will see it written with a capital P. And generally, we use our electrical measurements, right? We're going to use those SI or metric prefixes, and we're going to be using engineering notation. So it's going to be steps of 1,000. So 1,000 being kilo, a million being mega, a billion being giga, etc. Going the other direction, milli, nano, etc. I'm sorry, milli, micro, nano. Again, always steps of 1,000, or think of it as times 10 to the 3. Right? 10 to the 3, 10 to the 6, 10 to the 9, 10 to the minus 3, 10 to the minus 6, 10 to the minus 9. A little bit different than scientific notation. Lastly, we must have a complete circuit for current to flow. As a result, these are referred to as closed circuits, right? So if we're going to have a closed circuit, that's going to be circuit flowing. An open circuit, on the other hand, it means there's a gap in the circuit, so there's no flow. So we have infinite resistance, no flow. And then if we have a short circuit, it's usually something unintentional, something that we not really want to have happen. And that's when we have very little resistance. Maybe there's a break in the insulation or something like that. And we have short circuit, and so we have very little or no resistance. So those are the type of terms we used. Closed circuit, short circuit, open circuit. Should be familiar with those 3 different definitions. As always, if you have questions, don't hesitate to get in touch with me. Many of these are going to be well explained on the course space with additional videos, or through course reading the textbook. And as always, if you can always post on the Q&A discussion forum if you want to share your information with your fellow students.